Thank you, Lisa. Good morning, everyone. My name is Kate Riordan. I am a graduate student at SUNY Brockport, as well as a Technician 2 with Region 8 Fisheries. This is my master's thesis, which is in progress, but nearing the end, and I'll be presenting on a portion of it today. This thesis is a comparison of lake trout diets among the Finger Lakes using stomach content, fatty acid, and stable isotope analyses. So lake trout populations have varied among the Finger Lakes and varied across time. This data is from New York State DEC standard gillnet surveys, and it's represented as lake trout per net hour. And it has data going back to about the 1980s with time on the x-axis and the lakes in different colors. And we see currently lake trout populations are highest in Cayuga and Seneca lakes, slightly lower in Canandaigua, and lower in the remaining Finger Lakes. So we know that lake trout populations have varied across lakes in time, and so have the forage population. This data is from New York State DEC forage gillnet surveys, which are somewhat newly implemented only back to about 2017. And these surveys consist of a sinking and a floating net together to simultaneously sample benthic and pelagic habitats. Data is represented as average fish per set hour, which includes that sinking and floating net together. We see that for nearly all lakes, alewife are the dominant forage. We also see the appearance of rainbow smelt in Canadice and Hemlock lakes, some yellow perch in Canandaigua, round goby in Cayuga, and then we see Keuka Lake. Many of us are familiar with the story in Keuka Lake. Alewife populations collapsed around 2015. Since then, forage has been very limited within Keuka Lake. There are ongoing efforts to establish Cisco as a forage species in Keuka. Fingers crossed that it works out, but currently forage remains limited. So we know the lake trout populations, and we know the forage populations, and we could link those through diet quantification. And there's multiple methods for diet quantification. Each one measures diet over different time frames. Stomach content analysis measures diet over about a day. It's pretty straightforward. It involves the identification of stomach contents, which allows for great taxonomic detail. However, there could be uncertainty due to empty stomachs and unidentifiable prey. Fatty acid analysis measures diet over weeks to months, and stable isotope over a few months. These two methods are based on the transfer of biochemical markers from prey to predator through consumption. Those biochemical markers being fatty acids for fatty acid analysis and stable isotope for stable isotope analysis. For stable isotope analysis, we typically look at carbon, which indicates sources of carbon within the food web, with lower values indicating more pelagic, and higher values indicating more benthic, and nitrogen, which indicates trophic level, with higher values indicating higher in the food web. And because these rely on that transfer of biochemical markers from the prey to the predator, it requires that we know those biochemical markers of the prey so that we can see how they're contributing to that diet. It also requires that prey are distinct in their biochemical markers so that we can differentiate them. So by using these three methods concurrently, we could reduce the likelihood of over or underestimating prey contribution and get a holistic picture of the diet. This is all very important because diet provides insight into ecosystem dynamics. We can see how predators and prey are interacting within a given system. It could be used to investigate the impacts on populations of prey species. For example, if we're trying to stock a high trophic level species, such as lake trout, to control forage species populations, such as alewife, or vice versa, stocking a prey species, such as Cisco, we can see how those species are interacting within the system. It provides insight into lake trout nutrition. So if lake trout are relying on, say, an energy-dense prey versus less energy-dense prey that requires higher forage expenditure, it could impact the condition of those lake trout. It could also be used to indicate the presence of invasive species. There are a lot of times where first detections of invasive species, such as round goby, occur from stomach contents. So together, using these complementary approaches, we could offer insights into predator-prey relationships and inform fisheries management decisions related to stocking strategies, harvest regulations, and long-term fisheries sustainability. So my thesis has two objectives. The first is to assess lake trout diet within each lake individually and evaluate temporal changes. And the second is to compare lake trout diet among 6 study lakes using the most recent year of available samples. For the brevity of this presentation, I focused on objective 1, and I chose 3 study lakes, those being Keuka, Canadice, and Seneca lakes. I chose these lakes because their forage populations are quite distinct. As we saw, forage is very limited in Keuka Lake after the alewife crash in 2015. Seneca, conversely, has very high abundances of alewife. and brown goby were first detected in Seneca in 2023. And Canadice is more intermediate. It has moderate levels of, moderate abundances of alewife, has rainbow smelt, and somewhat of a mixed forage prey assembly. So all of my lake trout were collected by DEC standard gillnet surveys. I collected stomachs for stomach content analysis, belly flaps for fatty acid analysis, and dorsal muscle tissue for stable isotope analysis. I collected prey to use in my fatty acid and stable isotope analysis. These were collected by forage gillnets and electrofishing by DEC, as well as seining at SUNY Brockport. And I used whole fish, assuming that they are consumed whole by the predator, the lake trout. Stomach contents were identified to the lowest taxonomic level. I combined my data with historical New York State DEC data going back to the 1990s, and I quantified each prey item as either present or absent within a given stomach. Fatty acids were quantified using a gas chromatograph mass spectrometer. I retained 25 fatty acids for my analyses, and I performed multivariate statistics such as PCA and NMDS. And for these analyses, I included prey that occurred in 80 to 90% of those stomachs. And stable isotope samples were prepared at SUNY Brockport and shipped to University of Windsor, Canada for carbon and nitrogen quantification using an elemental analyzer. Because lipids could deplete delta 13 carbon values when carbon to nitrogen ratios are greater than 3.5, those values were mathematically corrected according to Post et al. 2007. I then performed Bayesian stable isotope mixing models using the MixIR package in R. I used trophic discrimination factors provided by Post 2002, and informative priors based on stomach content analysis using the Simmer package in R. So now on to the results. Starting out with Keuka Lake stomach contents, we see that for nearly every year, the primary content in the stomachs was mysis. We also see sculpin present in quite a few stomachs, and it's interesting to note that I mentioned in the collapse of the alewife population around 2015, we did see alewife in stomachs prior to 2015, but not posterior. We do somewhat see yellow perch filling that niche. However, there was no significant difference among years. Looking at fatty acids, just to orient you to these figures, for both these figures, one individual point represents an individual fish and the 25 fatty acids that make up its fatty acid signature. Proximity to another point indicates similarities in those fatty acid signatures. So lake trout were significantly different among years, and prey were significantly different among species. However, slimy sculpin and yellow perch did not differ. And when we plot them on an NMDS plot, we see lake trout are positioned somewhat between mysis and alewife. Looking at stable isotope results for Keuka Lake, on this is the iso plot for my model, and each of these individual points represents a lake trout, and these are the averages for each of the prey species. And this is the iso plot, so it's after those values have been corrected according to trophic discrimination factors. And there was no significant difference among years for lake trout. There was a significant difference among prey species, except alewife and mysis were not significantly different in their stable isotope signatures. And when we run the mixing model, we see that for all 3 years, mysis contributed most of the diet of lake trout and Keuka Lake. So we do see agreement between all 3 methods for lake trout and Keuka Lake, indicating mysis as a primary component. On to Canadice Lake. A major content in the stomachs for both years of data that I have was alewife. We also saw some charcids appearing in a lot of the stomachs. In 2022, we had also some smelt, some sculpin, and some more mixed prey, but there was no significant difference among years. Looking at fatty acids, there was no significant difference among years for lake trout. There was a significant difference among prey species, each one being significantly different from the other. And when we plot on our NMDS plot, we see that lake trout here are somewhat between mysis, alewife, and rainbow smelt, indicating they might be eating all of those species. Looking at stable isotopes, lake trout did not differ between years. Prey were significantly different among species, except pairwise, smelt, and mysis were not significantly different. When we ran the model, we saw that for both years, alewife and rainbow smelt were shown to contribute most to the diet of lake trout. In 2019, rainbow smelt had slightly more contribution, and in 2022, alewife had slightly more contribution. So here we see an agreement between all the methods indicating alewife present in the diet, and then we also see some other prey such as mysis, smelt, and some charkets. On to Seneca Lake, we see that for all years, alewife were a major component of stomachs. We also see slimy sculpin as a major component of stomachs. And there was a significant difference among years, that being between 1999 and 2013. And in earlier years, we do see mysis occurring in stomach contents, but we don't see that in later years. For fatty acid analysis, there was a significant difference among years for lake trout, except not significantly different from 2020 to 2023, but all other pairwise comparisons were. The prey species were all significantly different, and when we plot our NMDS, we see lake trout overlapping quite a bit with alewife. Onto the stable isotopes, we saw that lake trout were not significantly different among years, and prey were significantly different among species. And our model indicated that for both years, alewife contributed most to the diet of lake trout. So all three methods for Seneca Lake indicated that alewife is the primary forage in this lake. So in conclusion, each method did reveal similar trends in diet. We see mysis indicated in the diet for all methods from Keuka Lake, alewife for all methods from Seneca Lake. In Canada's, we see alewife as well as that mixed prey. The diet is matching up with that prey base, where alewife are abundant, such as in Seneca and Canada's. The lake trout are taking advantage of that. However, when forage is limited, the lake trout are relying on an invertebrate, the mysis. And we do see a little bit of a gradient there, so this is all the fatty acids for lake trout plotted in one figure. And we see the green here is fish from Keuka Lake, the purple here is fish from Seneca Lake, and then we see fish from Canada's in the center. So we see a gradient of that alewife utilization appearing in the fatty acid signatures. This all relates to the idea that lake trout are opportunistic foragers. They're consuming whatever is most readily available to them. And this could have impacts on the condition of the fish. So for example, where lake trout are consuming an energy-dense, easily digestible prey such as alewife, they can grow really quickly and get to large size. Conversely, when they're relying on mysis, which per individual there's not much energy and it requires a lot of foraging expenditure, they can't grow as big or fast and have lower conditions. So this is average condition for lake trout from each of the lakes, and you see it lower for Keuka Lake. So altogether, this reveals the importance of lake-specific forage bases in shaping lake trout diets and demonstrates the value of integrating multiple diet assessment methods to inform fisheries management. I'd like to thank Dr. Jacques Richard, my advisor, all of the past and present graduate students in Dr. Richard's lab for helping me to process my samples, DEC staff, particularly from Region 7 and 8 for collection of samples, my committee members for the conception of this project, as well as the Haynes Graduate Fellowship for providing some funding.
So you're seeing the centroids in the stomach contents, but not in the other tracers? Do you have any idea? Like, was it only a couple of them in the stomach contents, or why do you think you're missing that?
So, yeah, that is a tough one because they were appearing in some stomachs. Our sample size was not huge for that. We only had, say, 2 stomachs that contained, and 3. We did not include the centrarchid species in our analysis because we were primarily relying on based on the forage populations. So we could include those and see how it plays out in our analysis.
Any other questions?
For the lake trout that you caught, what was the size distribution of those fish?
So I only used fish greater than 350 millimeters because I wanted to just do adult lake trout. And some of them got quite big from Seneca Lake, but yeah, I did everything over 350 millimeters.
Any other questions?